is addition.
Okay. Yes, I got it. Please don't panic.
This meeting is being recorded.
No need to panic.
On the request by the speaker himself.
Okay.
Okay. Right. Yep.
Good. Good.
Maybe we could minimize that. Because it actually turns up. No, it's okay. Turn up as a black spot. Yeah, it's all yours.
Okay, thank you
very much.
Right. I don't know how to get rid of that top thing.
You don't. It's supposed to be there. I can move it to the bottom or to the side.
That's the bottom of the green part.
Yeah, the title of the talk is now covered, but I hope that doesn't mean that the rest of my title will also be some of it. Okay, in the name of God, the compassionate, the merciful. This is Hussein, as most of you know me. To meet new friends. Thank you very much for coming to my talk. I am today going to talk to you about a project that is being funded by this cryptocurrency company called IOG. And I work for them in addition to working for this university, this group in particular, Bergen Laboratory of Language Design, my other way, as an associate professor. This is both a matter of fun for me personally and money making, because they brought me to this. The process of having that fun includes doing work on Algebra and something else which is underneath. I can't recall what it was.
Algebra, statistics.
Right, statistics, yes, statistics and differential equation. Thank you for helping me on my own title. As you can see, I know my talk very well. Right, now, this is a research that was done by a group of people that we will collectively refer to as the Delta QSD team. That includes colleagues from a company called PNSO, which is a small Welsh company. Peter Van Roy, who was my host professor when I was a postdoc in New Zealand. Magne Mikhail, who sadly had to be in Oslo today, and then a number of people from IOG directly. This is our recent intern that we hired. What I'm going to present to you today is this paper, an extended version of it. That we presented in a conference called the ICE a few months ago in Portugal. Oh, this is wrong. It has to change. The reference is wrong, but what you see in orange is correct. Now, the first question that I would like to answer is, why at all would people care to predict performance? So we use the mathematics that I told you about to predict performance. This is specifically for software systems, but the paradigm that I'm formalizing for IOHK, now known as IOG, is more general. It's for systems development. And the idea is that we want to have performance aspects of systems development under our control. Now, imagine yourself having to look up weather forecast, and you go to the website, you try to find the forecast of today, and you find out the forecast comes tomorrow. Right? You know, it's just certain things have to keep up, and you can't like this. Bullet is trying to say the weather forecast that today cannot arrive tomorrow. Right? There are certain timeliness requirements that you need to meet. Without performance prediction, what generally happens is that you either get to re-architect your system, or you have to throw a lot of costly hardware at it, and you essentially don't have any control of what will be the outcome of the addition of the hardware. Our developments are actually on making this predictable, because we want to avoid those costs, and we want to figure those things out pretty early. So if you go to this paper of ours, you will be able to find an amplitude of examples where failing to predict performance cause people to lose massive money. Now, so I said that this research is funded by IOG. This is one of my co-authors of a paper called Kevin Hammond. He presented this talk in Lambda Days in Krakow in Poland, like I think like 5-6 months ago. No, was it June? Yeah, it was June. So your best bet for understanding why IOG wants to fund this research is this talk. But in short, IOG is this rising empire of cryptocurrency. They have their own network, which is called Cardano. The thing is that the effective operation of Cardano depends on the performance issues and their reliability. So that's when IOG called this Welsh company called PNSol, Predictable Network Solutions, that are a world-leading performance company, and they're so they had decades of history about making performance predictable, but their intuition was never really formalized. So they hired me to formalize their brains, and their kind, and that was how Delta QSD came out. So if you'd like to learn about Delta QSD, the best resource that we have at the moment is this tutorial by Peter Van Roy, presented in Discotheque last year, which is available online. I am today going to only tell you about how it meets timeliness and how we use those three pieces of algebra, three pieces of mathematics, three fields of mathematics to help formalization of timings. So without any further ado, I would like to define what we mean by timings. I'm going to read to you that definition in the box. Timeliness is delivering results within the required time bounds, and in case that is not clear, sufficiently often. And so it's not something that you do just once, something that you would want to do all the time. You want it to be within the bounds all the time, or at least, if not, no, not all the time, sufficiently many number of times, right? Now, so here's how we picture that. There are very few things that at this point I am requiring you to understand. We will get more into this later. The thing is that, let's say that you have a requirement that, let's say this is somehow a plot of a requirement, so the required timeliness behavior, and this is your observed timeliness behavior. If by some measure that we're going to talk about, this is better than that, then you're timely enough. Right? We'll see more of this. Don't worry if you don't understand more of the.
It is higher up in the diagram.
Well, better than means higher and to the left. Right? Intuitively, that's so if it is higher, but they still coincide, they collide, then we have some problems. So if it's higher and to the left, then we're safe, right? And now, so the formalization of delta stream starts with outcome diagrams. I am now going to give you an example that some of you might be very familiar with. So let's say that we have a caching system. Excuse me, sir, because I don't know you and you, madam. Do you have a background in computer science? So we know what a caching system is. Very. So now systems engineers are very familiar with what is called block diagrams. Block diagrams. This is how they describe a caching system. So let's say that there is a cache that is an element in our system. Someone sends a read request. That read request has two possibilities. It's either a hit, in which case we just we have the local information, we return it, or it's a miss. If it's a miss, then we go make a lookup, but through network. So we go through the network and we come out of the network after performing the remote lookup. And all of this is actually controlled by a timeout, right? Depending on the results, we return what we've got from here, right? This is a very intuitive yet very imprecise explanation of the system that we're going to model today. Now, I am going to now develop step by step what we call an outcome diagram of the same system. Now, an outcome diagram for, let's say, only for the moment, only the possibilities of observing a miss or a hit. Right? So that would be what we call, this sign here is what we call a probabilistic choice. So we would say that it's 95% chance that we have a hit, that's cache hit, C hit, and 5% probability that we have a miss. Okay, now we present that using this outcome diagram. In this diagram, these are outcomes, right? These are operations on those, or operators on outcomes. In particular, this one is probabilistic choice. Now, I'm not going to talk about these ones today, but those are called observation locations. Now, important things to note. Our definition for what an outcome is that an outcome is what the system gains by performing one of its tasks. And in particular, an outcome is not a system state, it's not a subsystem, it's not a class or an object, or any of the commonly used, for example, UML diagram things, right? Now, we get a lot of confusion from the people who do like state-based exploration of systems, like model checking people. Because this is being recorded, I need to emphasize that these are not system states, right? These are outcomes with that definition which I just quoted. You. Are we clear thus far? Yeah, very good. Now, so provided that we have a miss, we want to perform a lookup into the main memory. Now, what you get here is that I'm refining the previous outcome diagram, which is the one that you've got here, into this one by adding this guy to the end, and this is what we call sequential composition. Now we have this convention that if if an outcome is connected and to the left of another outcome, it means that the right one is causally dependent on the left one, right? So this is showing causal dependency. Now, and then, so when you perform a memory lookup, there is always the error correction that might fail. In this particular case, we are taking the possibility of failure to be with the rate of 1 to with a weight of 1 and 10 to the minus 16, right? So only very rarely does the error correction fail, right? And as you can see, this is modeled again using a probabilistic choice. Now you want to make sure that this is properly timed. So what you would do is that, so this is the component that we saw before, or another a part of that. Now the fact is that before we do that, we go through the network, and after that we come out of the network. But all of this needs to be timed out, which leads us to this new guy, this new operator, which we call aim to finish or first to finish, which means that if this outcome diagram, if this bit of the outcome diagram finishes before this one, it wins. If it finishes after that, this one wins, right? Now, so that's our time-bound network connection. But now we would like to take a closer look to the highlighted part. Right, I think I went ahead of my slides. Now, so, okay, so we need to now explain how we make use of these outcome diagrams, right? In order for that to happen, we need to kind of have a language for expressing ourselves in terms of algebraic expressions and all that. So I'm going to just tread the same path, but this time with the expression. So we explain this outcome diagram using names for outcomes, for individual outcomes. Like this bot thing, bottom, is for failure, right? This is saying that there is a weight 1 for the main memory to succeed, the look of the main memory to succeed, and the chance of, or the weight of 10 to the power of minus 16 for a failure of that, right? Now, usually at this point, when I see this many warnings in the classroom, I ask people to tell us jokes. I hadn't asked anyone to do that in advance, so I'm not expecting. But if anyone wants to volunteer, we will welcome that. Thank you for smiling. Now, so now we're going to make we're going to refine the outcome diagram. So as we're doing that, these are our signs for sequential composition. And I'm guessing that you can follow the connection, right? And then as we do the timeout, so it's a race between the upper line and the bottom line. That's shown using this sign, which means that these two are being run in parallel, and any of them to finish will win, right? Or concurrently, and any of them to finish will win. So you do that another time, you get to this larger expression. I'm not going to delve into the details of it. The minor difference here is that the probabilistic choice that you see here has a slightly different notation than here. This one has weights for each side, whereas this one has a percentage, and that's why we use the notation of the what's called angle brackets. No, it's called square brackets. Square brackets, which shows that this is the percentage of the times that this one will succeed. Now, so where's the algebra that I promised? Now here's where the Delta QSD, the Delta Q systems development. I think I actually never told you what that stands for. Oh, I'm sorry. Yeah, that was my mistake. Here's where the Delta Q concept comes in. This is a key point, right? So I need your attention. So Delta Q is also known as quality attenuation, or a measure of delay and failure for each of the outcomes. So imagine that you are the post office and you have letters that are assigned to you for being sent to Oslo from here, Bergen, right? If your statistics, for example, tell you that 95% of the time you can deliver within half a day to 2 days, and maybe 4 extra persons you need another day, and maybe 1% of the cases you just lose the envelope that was given to you. Now, that is a measure of the delay that performance of that task takes. And it also has a small fraction which states the measure of which measures the rate of failure, right? The failure rate. Now, that is the concept of a delta Q. Now, we represent that using what is called an improper random variable. And we usually work with, depending on the operators that we would like to use, we usually work with CDFs of those. So it's a random variable, it has a CDF, it has a PDF as well. You integrate over one, it's the other. You derivate over it, it's the other.
Try to explain what you mean this diagram.
I'll get to that.
Should percentage be probability?
Yes, that's a very good guess. I'll get to there. Before I get to there, the thing is that, so improper random variables are rarely known because most people consider them defect, right? The thing is that improper random variables don't need to make it when you integrate over them from minus infinity to plus infinity. They don't need to necessarily make it to 1. And this small fraction, this small, difference between the topmost cumulative mass and 1 is what is referred to as the intangible mass, and that is how we model loss at the same time that we model delay. Now, this is something crucially important to the concept of the delta Q, and it's one of the most important developments of PNSOL. If you take a look at the models of performance if you take a look at the performance models that are around, rarely there is anything that can integrate these two together. In fact, we are not aware of anything else. Right? Now, more into the plot. What this is saying is that the probability of a delay of amount d is p %. Right? And it's also saying that there is this much probability for failure, for the delay to be more than what we can afford, right? Which we consider failure. For example, there might be a letter. There was this thing in the UK a few years ago that a letter made it to the address that it was posted to, and the letter was posted before the World War II. So that's still delivery, but I'm sure that for a lot of cases that is considered to be failure, right? yeah. Postman pass. It sometimes doesn't do its job very well. Yeah. Now, so okay, how do we model the timeliness? I am going to give you a few squigglies. You're not expected to read through the squigglies, but I will give you some intuition. This is the formal definition that says in lay English, provided that you give me delta Q assignments for the individual outcomes, this formulation tells you how to accumulate those individuals and work out the total delta Q, right? Now, the formulation is as such, right? As you can see, it's full of squigglies. My apologies. Do you guys have any background in logic? You guys I know, but for the new friends of ours, you have any background in logic or? Very good, very good. Madam?
Not so
Okay, okay. And my apologies for hurting your eyes. I am now going to focus on this one in particular. What this is saying is that, let's say that you have a probabilistic choice between two outcomes O and O prime with the weights M and M prime. So with the weight of M, you go to this side, with the weight of M prime, you go to this side. And there is some guy who gives you individual delta Qs for the compartments in O and O prime. Then, using this formula, you can calculate the overall delta Q for this entire expression. Now, what does the formula say? It says, do this one first, proportion it according to the weights, plus do this one next, proportion it according to the weights. Right? It's a weighted sum. Right? Very simple. So yes, the notation is intimidating, but the mathematics is quite simple.
Can I just interject something?
Please.
Because what basically is happening here is that we have variables on the diagram. And the diagram, the outcome diagram is syntax. And the variable is some distribution for the components of that syntax. The delta zero assigns a certain distribution to the outcome, to the variables of that syntax. So that's our alpha in the theory downstairs. This delta Q is the semantics. The semantic bracket is the semantics of the outcome decomposed into the different places that form the outcome diagram, the syntax of this language for specifying, what do you call it? Performance
specification, yes, performance specification of the system too. Yes, yes, that's right.
So it's basically the theory we're developing, but just phrased differently for a different kind of example.
Yeah, we logics people like to intimidate people with our notation. So that's what's happening.
You said it's kind of a weighted sum.
That's right. Yeah.
Is there a relationship between M and N prime?
There is no assumption on that, but there can be, and there is no problem. But this formulation is not assuming anything on. But these can be functions of one another. These can be functions of other things. Right? There is no assumption on that.
Can M always be implicit?
So yes, that's true, and they have to be non-zero, but they don't need to be a single number, right? And they don't need to be non-correlated. There can be correlation between M and M prime, right? Is that answering your question?
But in ideal case, like it should be the sum should be less than 1. Both of them.
The sum will not be less than 1. No, because these are weights. So, for example, M and M prime, if there are numbers, can be 2 and 3, right? Which means that with the weight 2, there's the possibility of choosing. There's a probability of choosing O, and with weight 3, there is the probability of choosing O prime. Now we do have the alternative notation, which is the one that we put in the square brackets. That one is percentage, and that one what goes. We only put the one above because then the sum is 1, and you can always work out the. That's percentage, and these two notations are interchangeable. You can always work the weights from the percentages and the other way around, right? Did I now? You know. Now, so I had an example, the running example, the cache example, right? Now, provided that you have this delta naught, which gives you delta Q values for the individual outcomes of your large outcome expression, then you can use the formulation that I showed you in the previous 2 slides to work out this overall observed delta Q for your modeling of your cache system. And yeah, there is abbreviation. So there's a let's binding here. There's a this guy delta Q mem itself is this, right? And so getting back to the diagram that I showed you, that means that if, for example, the required delta Q is as follows, which is this one, right? The dark blue. It says 50% of the times the query should be answered within 5 milliseconds. This point, 5 milliseconds for 50%, right? 95 of them, it has to be done within 10 milliseconds, which is here. 97% within 15, which is here, and 3% are allowed to be lost, right? Now, if the delta observed that we calculated here, delta Q observed, according to this formulation, is giving us this black one, because we are above and to the left, right? We know that the design that we have had in mind has no predictable infeasibility, right? Please mind the precision that I'm putting into the accuracy that I'm putting into my phrasing of the term. I'm saying that there is no predictable infeasibility, right? Which means that we can't, at the moment, with the given pieces of information, predict that this system with the design that we have in mind is going to be infeasible, right?
this is a negative negative, it's a double negation. It's not a positive result. So you told them about the contrapositive and the no,
Really?
no, okay. Well, so it doesn't really imply that the system will be feasible. It's just saying it won't be infeasible as far as I can see. Right? Now, I have a still show. Yes, I have a joke here. So once upon a time, there was an engineer and a physicist and a mathematician, passing by a sheep farm. The engineer said, "Are you an engineer? Did you consider yourself an engineer?"
Practically.
Okay, okay. Please don't be offended. This is not intended to offend. Okay, okay, good, good. So you have a good excuse. Right. So the engineer says that sheep is black. We conclude that all the sheep in the world are black. The physicist says. We conclude that there exist black sheep in the world. The mathematician says we conclude that there are animals in this world, one-sided which are black. Right? So I saw you down, pointing out. Yeah, I thought that's a good time to. Yeah. So I haven't still shown you where the algebra is. I showed you some algebraic expressions, but I didn't show you where the algebra is. Now, so I take it for granted that you know that this expression, with the details of which you don't know at the moment, can be obtained from the diagram above, right? With that assumption, we can actually do certain algebraic operations on it. And those pieces of algebraic operations are valuable for the reason that I'm going to tell you. Now, so this is, I think we have one step. No, this is the exact same expression that we saw in the previous slide. Now, the first thing that we would like to do is to reassociate this expression so that now the pair of parentheses are on this side rather than this. Right? Then we would like to do something similar for this pair of parentheses. So we move the pair of parentheses in a way, reassociate that so that it's on this side. And then we get this bottom sign at the very top, right? With some Q, which is the percentage of which is the rate of success for this design, right? And that is very important because that means that I can work out the rate of success of the design that we have in mind. Now, in this case, the rate of success is huge. You know, as an engineer, I'm sure you can. This looks more or less, you know, unworldly. So Ericsson has this product which they boast all the time about, and it has 9 nines. Right? This is 17 nines. So, but the piece of information that it is giving to you is actually more valuable than the data itself. What it says is that if you were expecting a rate of success that is higher than this, the design that we showed to you is not going to get you where you want it to be. Now, we obtained that information, that piece of information, by only drawing a number of diagrams, which quite frankly can be done on half of one side of this thing. Right? That's around, I don't know, like maybe 5 minutes
of drawing. And we obtained this result. Now imagine what would have happened if we would have built the system. And we realized, oh, it's not giving us the performance we wanted, the timeliness we wanted. What would have we done? Right? Could we simply thrown more hardware at it and expected it to work? Could we completely re-architected everything and expect it to work? These two are questions that PNSOL is an expert on, using Delta QSD, right? And now the formalization helps them to actually do the kind of algebraic manipulations that I told you. Now, the reason why we can do those algebraic manipulations is because I have proven them, right? Yeah. Now, here's a bit of algebra. This is with my education. That was high school algebra. So I think that some of you might be able to follow that. Yeah, this is a table of with which operator makes which algebraic structure, right? Now, unfortunately, these are very weak results because there is the associativity fails and you know the entire algebra gives up, right? That's one thing. Right. The other thing is that we can't form algebraic structures for exactly the same reason that there is no associativity. We can't form algebraic structures which include more than one of the operators, right?
Just
Please.
this is sort of what will be covered today.
Very timely.
And stuff going on. And compatibility is acceptability. Yeah. And magma just needs a binary operation, which is
Closed under. It's just closed.
yes,
Two things as well.
Two things, the result gets into the same set.
yes, this is just a type declaration.
Yeah.
Okay. Yeah. Right. So, amongst other things, I have proved these identities. Sorry for all the intimidating squiggly notations. I am going to pick up this one in particular, which says if you perform an outcome and then fail, it will be as timely as failing itself, right? Which is like this. So in the case of the cache system that we were speaking about, if it happened that this guy fails, the entire outcome fails. It's just as untimely or timely as it would have been if this entire thing would have been just a failure. But by the way, we call the bottom sign is called unconditional failure, and this one is called success or perfection. Sorry, it's called perfection, and the sign for that is top. Now these identities that I proved, they have been in use by PNSOL for quite some time, but they didn't have any formal proofs of them. Now, for your information, and this might, as an engineer, not really interest you, the proofs of these mostly are relatively routine. And for those who remain after this presentation, I will show some of the proofs because I promised 3 fields of mathematics that I have only touched on 1 of them, right? No, 2 of them actually. I did show statistics as well, but I haven't shown differential equations. Now, Right. So these are the identities, or the identities that we used when we were reassociating some of the cache examples, right? Okay. Now there are also distributivity results. I'm afraid these are the only distributivity results. I'm going to read that for you. What this is saying is that observing time, and this is meant to be the vernacular, yeah, observing time, O combined with any of these three operators with a probabilistic choice between O2 and O3, you can distribute that same operator between O1 and O2, and then between O1 and O3. Right, this is what it's saying. Now, unfortunately, there are only 3 out of the 15 possible that hold. A lot of the paper, the ICE paper, actually is devoted on proving that the other 12 do not hold. Right, that was the more difficult part.
And just an interjection again. Binocular time is just the information.
Thank you. You have been very timely with the presentation of these things. Thank you very much. That's such a coincidence with the timeliness focus of this talk. Yes. Thank you. Now, so in summary, we have a Delphi QSD team which works on the formalization of the paradigm. This is an ongoing project funded by IOG, and we wanted to have the algebraic manipulation because we are working for tool support for it. And one of the things that is giving us tool support is a Magnolia implementation of that done by Matney. We also have a Jupyter notebook that our intern has developed, and you guys will play around with in 329. I believe. Yeah, there is an A as well. Yeah. I don't quite know what that A is, but I hope that means that there will also be a B where I can teach you more advanced things. Yeah. Yeah. Now, a lot of the paper is devoted to this thing called properisation. In the talk that I was giving in the ICE conference, it was half an hour. I believe we have had way more than that now. But I didn't have to show, I didn't have time to show properisation. There is going to be some training available, so for those of you who are interested, I would be very excited to teach you, not teach you, explain to you properisation. And the thing is that this is the first body of mathematics for improper random variables. For some reason, people just thought that would be defective. They threw it away. But now there is research. Okay. Questions, please. No questions. Shall I be pleased with myself and take it for granted that I have already answered all the
Oh no, I can't with the pleasure. Sorry, I'm sorry. How do you relate the quantifiers that you have above the magma to, I guess, regular quantifiers? Or are those just symbols?
Right, they are just symbols. They are just symbols. So the idea is that if I can go
new binary operators.
yeah.
So they don't in any way relate to.
No.
Okay.
No, I mean they have what do I say? They have intuitive connections, but that's not because they are defined in terms of it, right? So the idea is that when two outcomes are combined using this, they are run concurrently, and the combination is done when both of them are done.
Oh, okay.
So
Whereas this one, the two are run concurrently, the combination is done as soon as any of them is
Yeah,
done.
yeah.
So that's why we call this one all to finish and this any to finish. There is also older terminology for this, which says that this is first to finish and this is last to finish. Yes. Right? But I tried to change that terminology because I think that this is more intuitive. Yeah. Any other questions?
it's just interesting how fancy names you can give binary functions.
That's right. Yes, and also fancy looks. Yeah, it was this one I had to combine the three. So this is a bullet followed by this arrow followed by a bullet, and I had to get the spacing right so that it looks like one operator. Yeah, fancy looks, fancy names. Logic people, you're very proud of them.
Very appreciate it.
Yeah, okay. Okay, now, I had promised differential equation. In if you need to leave, this is a good point. If not, I can go into the differential equation. No? Okay, now I am going to stop sharing for a moment.
Did you press the one button?
I did twice. Okay, what I'm going to do is just
So classical mathematics is sort of doing this all the time. And then if you try to sort of erase the connection to the real numbers, then we sort of get things like abstract mathematics structure.
right now. So I would like to start by showing. Well, maybe I should just briefly show this diagram that I didn't have in the presentation. So yeah, this is the catch example. We are introducing the failure rate here, which is shown by box sign near the bottom sign. Then we are using our algebraic notation, our algebraic manipulation to get this dot out of this zone. So that would become this one. We get it one level further off, which becomes this one, and now this is the same as that. Right. Now we can perform this operation because there is a theorem that I have proved, which is called the properisation theorem, which in short says that if you know the failure rate of this guy, you can manipulate the CDF of this in a way that it is no longer improper, but represents the intangible mass as a probabilistic choice between the properized version of the same outcome and the failure. And then we have other theorems which then help us to bubble up the bot to the bottom to the very top and quickly work out the success rate or the failure rate of the system. Right?
Just wait a second here. Because you see that there's sort of two probabilistic choices. Sequence, you could make that into ternary probabilistic choice or a list of.
By just continuously applying.
Yes. The thing is that these are magmas, so you need to reassign all the weights on them to sort of map different weights to each of the branches.
Yeah.
Well, if you do something similar with sort of first to finish, last to finish, they are associative, so that means you can just Is that enough? And then you can check to reduction operation rule and
Yeah.
So it's already you see that these properties that's proven in this paper really helps us in the computation of these things.
And that's what we mean by developing an algebraic backbone for a tool. So if we want to have a tool, then the tool better build on these theories.
But what you're saying here is that you can go from an improper running variable to a proper running variable by moving bottom to the outside.
By showing that, by representing that as a probabilistic choice.
Yes, because then you pull in all of statistical theory.
That's right. The standard theory of statistics. Yes, correct. Yes. Okay. Now that's our take on statistics.
Yeah, but they will be right use.
Yeah, always just rewrite this.
Yeah. Okay. Now the laymost way of proving things is like this. So suppose that out of the these identities, we have chosen to prove this one in particular, which is saying that a probabilistic choice between failure and failure is still failure. The way to do that is to say that, look, these guys have similar delta Qs, right? Now, the way you do that is that you work the delta Q of one side, and you show that that's the same as the delta Q of the other side, right? Now, that is the most basic way of doing that, but it's unfortunately this basic and easy way of proving things doesn't work all the time, right? That is how, for example, or why, for example, I needed to develop this entire properisation theorem to show that the other 12 distributivity results do not hold. Right? Now, let me show you some differential equation because I have made it great for so long. Now, suppose that you want to prove or disprove this identity or alleged identity. Then the way to do it, as I explained, the most basic way to do it is that you start by working out the delta Q of one side, and you hope that you can show that that equates to the delta Q of the other side. And if you do that, then you will end up with this differential equation, which we didn't know how to prove or disprove. Right? Now, what I have shown is that this cannot hold in general, right? By showing that this identity does not hold in general, right? So I proved this identity. But we know, therefore, that this differential equation does not hold in general, right? But there might be, and we are hoping that there are, solutions to this differential equation. And if you know someone who can help us with that, please bring them on. Okay? Please bring them on. Yeah. Now that's my apologies, but that's all the differential equations I'm going to show in this talk. If you're interested, I would be excited to show you some properisation and some more of our proofs. If not, this is a good time to.
But you promised us cryptocurrency and not to earn big amounts of money.
Did I promise the second part? Right. The first part, I think I did realize my promise because I said that this is the company that is funding it, and that's Kevin Hammond's talk on why it's funding, and that's why in short they want it. Yeah, so I think but I can talk more about it if you like. Now let's see. So I had two techniques for proving that that those remaining 12 distributivity results don't work, at least in general. One of them is what you guys are familiar with, which is counterexample. So I worked out specific combinations of constants in the algebra that show that the two sides of the alleged identity do not equate. So in particular, for this one, I disprove this by this counterexample. So I take O2 and O3 to be taught, which is also pronounced fraction. I assume that this one has one distribution, and then I worked out that on the one side that equals to delta 1, and on the other side it equals to yeah, 2 delta 1 plus delta 1 times delta 1 to the power of 2. So leading to this equation, which then means that O1 has to either be bottom or top, right? Which means that doesn't generally hold. So that's one way of disproving things. But the major development of this paper is in properisation. Now, in late English, the major result of the paper is this, which says if you have if you would like to examine the equality of O1 and O2, you can examine it by properizing the two sides and seeing whether the properized versions are equal. Right? Now, that helped with the proof of right. Now, I'd like to show you a lemma here, the proof of a lemma. So let's say that we are proving one. Let me see whether I have. No, this is not the right proof. I'll just show you another.
If we can automate this proving in the magnetic sector, if my formalization is reflecting necessary details, it would be very nice if there's a proof that we can see that it actually gives the same result as this.
Right. Here is a proof of when you have a sequential composition of something that succeeds with a rate of 8% and something else that succeeds with a rate of 2%. So you can perform these manipulations, which is the first of them is distributing the right component into the left component from the right, and then once we're here, we want to again distribute this O2 into that parentheses, and then we take we kind of reassociate this expression, and we get to here. What that is saying is that if you have two outcomes that are sequentially composed, and each of which have a rate of success of A and B, the overall rate of success is A times B. Right? And this is the kind of algebraic manipulation that we have. And as you can see, the proof steps do not involve going under the hood of delta Q itself. This is algebraic manipulation. Right? Now, with this kind of result, right, too many boarding passes of mine. Shared it with everyone on the internet. Right, let's see. So that's the result that I just showed you the proof of this one. Right? Now, I'd like to show to you something about properisation. So, let's say that we want to disprove this identity. The way to do that using properisation is to show that the properisation of this side is different from the properisation of this, so that we can use the contrapositive of the properisation theorem. Right? So the properisation theorem says if two things are equal, their properizations should also be equal. Now we're saying two things are not equal because the properizations are not equal. Right? Now, and in particular, we show that the rate of the failure rate of the two sides are different. Right? That is why we keep playing around with the bottom side all the time. Right? Now, so if we properize this side, we get to something like this, where P1 and P2 and P3 are the rates of success. Rates of success for O1 and O2 and O3, respectively. And you do the same on the other side, you get to this huge expression. And if you bubble out the failure to the top level for the expression at the left-hand side, you get to this one with the percentage of Q equaling this. And if you do that for the right-hand side of this inequality, you bubble out the bottom side to the very top level, you get to this expression with R1 and R2 being this, which means then that this expression needs to, this equality needs to hold, and that is not something that generally happens. And that's how we prove that the two sides of this inequality are in fact not equal. That's how properisation is. Now, this is how I kind of figured out a lemma for disproving things, but properisation is something that in practice PSO has been using for a long time for quickly working out the failure rates, as I showed you today. Right? But the formalization was never there. In fact, I proved that action of theirs is is correct. Now, that is pretty much everything that I want to